Hi everyone, so today my topic is efficient JIT to 32-bit arc. So the background is, so generally at the moment the eBPF ISA, by default it's a 64-bit register, and the current LVM code gen is using the 64-bit register by default. So there is actually no big impact on the 64-bit architecture like ARC64 or ARM64. But for the 32-bit architecture, for example, ARM32 or the NFP, actually we need the register pair to model the 64-bit register, and also we need to generate extra instructions to operate on the, always operate on the high 32-bit. So we really want to optimize the JIT compiler for 32-bit architecture. And actually you could see from the real program, I benchmarked the load balancer and the XDP load inline. You could see a lot of operations actually it's natively operate on the 32-bit types. So there is a big opportunity that we could reduce code generation. So the first approach we could use is we utilize the existing eBPF 32-bit subregister ISA. So actually, since LVM 7.0, we could specify this ALU32 option that could generate the 32-bit subregister already. And but now the issue is during the JIT compilation, can you generate the native 32-bit instruction when you say ALU32? I think the answer is no, because currently the ISA specification is whenever you write to the low subregister, actually it requires you automatically zero the high 32-bit. Actually, compiler or the assembler writer, it could possibly exploit this. So for example, this C program, you could see it's unsigned 32, then it's write to unsigned 64. Actually, the code generation, it's using subregister, then it's using the full register directly, because the compiler is assumed the high part is implicitly zero extended. So therefore, for the JIT compiler to safely JIT a single 32-bit instruction, you need to make sure the result of ALU32 instruction is really referenced by the 32-bit use only. So we could, one solution is we do this in the verifier. Generally, we don't do the extra code gen for the ALU32 destination, but when we do an instruction scan, the first time we see a dist rake of ALU32 is used, we mark it, oh no. When the first time we say it's used as a 64-bit use, then we mark it as a 64-bit, which means it requires zero extend. Then we keep this marker, then later it's used again. If it's not killed, it's not destroyed, then it's safe. You don't need to do zero extension. So this approach, the issue is we always need to generate extra zero extension when there is a mode switch. Generally, when it's switch from 32-bit use to 64-bit use, while then we need to define for which case such 64-bit use exists. That's currently it's jump, because we only have jump 64 and ALU64 and wide store. So I benchmarked the jump situation. So generally, for example, the XDP load inline and the load balancer load inline, the total instruction is the number, then you could see the jump instruction is roughly 10%. And if I have a local change which enable the jump 32 instruction, you could see actually more than half of the jump instruction could be used jump 32. So I think if we introduce jump 32, then could largely reduce the place that leads mode switching. And also, but then there is a big problem, that is if there is no flow analysis, when the one instruction is a jump destination, that means there may be multiple defi merged to this instructions, and we don't know whether there are some register which is not marked as, which is not, there is no extra instruction generated to zero extended it. So we need to be conservative. That is, whenever one instruction is a jump destination, we always need to clear all the 64-bit marker. Generally, all the following use lead to regenerate the zero extension. So the other solution to reduce this is actually LVM. I think it has better knowledge of all those things. So probably we could modify the LVM backend, generally remove the exploiting pattern to let the backend generate the implicit zero extension, always generate the zero extension explicitly. And then we need to introduce, I think, a new instruction for the on-site extension, because currently, even though the move is implicitly doing zero extension, but by doing this, actually we want to remove the implicit extension. So we really need a new instruction for this, I think. And now the big problem for this is there is no security guarantee, because you can't guarantee the verifier actually don't know the input sequences is compiled from LVM compiler that conform into this convention. So even though the compiler could generate an AF tag, like ABI tag, to tell the verifier, but this tag can be faked, so we are not sure it's safe or not. So I think it's a potential risk. Then I was also prototyping some other approach for the 32-bit optimization, that is the standalone data flow analyzer. Generally, by this way, you don't need to know whether you don't need the 32-bit instruction, or it just does everything from scratch. So it's quite heavy, actually. So there's two ways. One is optimistic, the one is pessimistic. So the first, I think, generally for a local analyzer for instruction sequences, if you know there is a, whenever you find a 32-bit use, you then go back to its defi. Then you double check its defi. If the defi has a single use, which is this 32-bit use, then surely it's 32-bit safe. And you could see without ALU32, we can only know 32-bit use from the narrow store and comparison using the range information. If it's zero extended, then probably you only need to compare the low half with 32-bit use. But the whole thing is not good for very few opportunities. And with 32 bits enabled, the code generation enabled, you could see there are much more 32-bit use. Actually, and it could let analyze finish quicker, because sometimes first single pass scan, you could conclude that it's safe. While you see the 64-bit situation, the first scan, you only know R2 is 32-bit safe. You need to keep going to, once you know a defi is 32-bit safe, then you iteratively check its use. If it's, because now it has a defi use 32-bit, then you check its use. If the user has a single defi, that defi is 32-bit safe as well, then you go back. So it's slow. So I have an algorithm which is pseudocode. I think it's, I won't go details to this. I think it's pretty much very simple. It's just the df init. Generally, you do the scope partition to have a basic, there's no full control flow, but you generally mark the branch, introduce unknown defi, introduce unknown use, those things. Then you build the DU chain in the df pass 32-bit safe. Then you copy some analyzed result. Then you pass to the JIT backend. Then you release resources. So, and also this could potentially extend it to a global optimizer based on what I think Jiong introduced. There was a CFG infrastructure. We could split the register info to the high-low part, then build the live in, live out for the high part. then use the classic live variable analysis to do backward analysis. Then we could know the live out of a basic block, I think. So that's ideally, I think, a standalone DF analyzer. It's sitting inside the color lab, could be reused by any part inside the color or inside any tools which sitting in the color tree. So the library could be compiled for both user mode and color mode. So whenever you need some instruction analysis, you can call this library. It offers some optimization paths, generate some information for you. Yeah. So then there's a third approach for 32-bit automation, that is reuse the verifier DF analyzer. Currently, the verifier has a powerful, but not powerful. It's a night data flow analyzer. It's designed to release more prune opportunity for the past pruning. Actually, so it's generally it collects the register user information in a state, then make sure if some register is not used in later state during the state comparison, you don't need this register. It's safe to ignore it. So I was thinking extend this infrastructure to recode the 32-bit use, but it's really hard. That's because the 32-bit RAID is unlike the typical RAID. It can propagate. Generally, you have once you find a 64-bit RAID, you go to its define instructions, then it will propagate to the use of that instruction. So it's very complex. The whole thing is a mess. So I think I won't go details to this, but I have a very detailed slides to introduce my algorithm, and I benchmarked this on my machine. It could correctly mark most of the case, but I still got one color case doesn't work, which maybe could tell there is a big issue. So what I want to say is the 32-bit approach. Now I think there are probably three approaches. One is the verifier based, but I think probably the verifier is better focus on verification, offer reliable and fast verification, no bother the optimization. The second is a classic CFG DF analysis, but it's not, maybe it's too heavy for the kernel space. Even though it's reliable and has a very sophisticated algorithm. The third is we reuse the LVM result and pass those results down through the 32-bit sub-rig ISA. I think this is a good way because it's throws the heavy lift work to the user space compiler, and the compiler is really good at that. We don't need to reinvent the where. I just reuse the compiler results. Then this approach issue is a lack of some instruction. For example, jump 32, which is causing trouble. Even though we can work around, but it's not ideal. So I kind of feel maybe the best approach is we just reuse the LVM information, then enhance the ISA. So that's what I have done and experimented for the 32-bit optimization. So yeah, any questions?
Can you go back to the last slide, perhaps? One more. Keep going.
This one?
One more back.
Keep going.
Right. Keep going. One more. Sorry.
One more.
One more. Oh, okay. So I get. At some point, you were doing the propagation backwards.
Yeah.
And the thing you were just tracking. What were you doing that for? I missed the.
I think this was to explain. Mostly, I think the propagation is easy. The difficult part is the path pruning because because I use this existing infrastructure, because we don't need to build a CFG because it's literally speaking working all the possible paths. But then there is path pruning, so sometimes it works paths, but then it doesn't keep working. Then you need to propagate those 32-bit use back to the state.
So is it basically like a scalar evolution kind of thing? Does that make sense? I have to look at it, I guess.
Sorry?
I'm going to have to read the algorithm in the code.
So can you go back one more slide?
This one?
More.
Oh,
Just this one. So yeah. So when I was looking at it, you also had one very interesting idea, like few other slides before, when you were saying to split liveness instead of one register into high-low. If you combine the ideas, will it work? Like if you do this, yes, so high-low and liveness to instead of, so currently liveness is only done for the full register, but if you do both this high-low split and combined with the stuff that you're doing there, can that work?
I think it's hard. Mostly, generally, when you're reaching one instruction, when the verifier execute one instruction, you don't know it's requires 64-bit or not. You must keep working to a point, to an instruction which really is access 64 bits. Then you need to propagate back. Then the problem is it's a runtime. It's an instruction worker, so you need to remember lots of historic information, like which instruction has been worked. This instruction has contributed to the value generation of one rig. Then the second instruction contributed to that as well. Then you found one 64-bit. You need to propagate back to this instruction. So I think that's the hard part.
Yeah, so for liveness, we kind of do what you're describing already. It's just this current liveness, there is a pointer chain for all the liveness. It's missing the actual instruction. I think that's what you're referring to, like where it was defined, but that should not be, well, overly complex to add. And like if it's combined with this high-low stuff, then you will have a separate chain of like walking back for just the low bits and then the upper bits. And once it's done, like once all the verification is done and all the liveness is done, you have all of these chains built, so they're still in memory. So at that point, there can be like another pass to walk this only high-low pieces. But like this of course like would require the changes to this jump 32 that you mentioned. I think that's, well, necessary first step regardless.
Yeah, so actually I was benchmarked the jump 32. It can reduce code size for 64 as well. So if you enable the march equals area 32 for the ARC64 for x86, it's using the sub-register, right? But now because we don't have jump 32, so for the 32-bit jump, we are 0x10, something like that. So we have a path to people to combine some situation, but we can't do all. If we introduce this instruction, actually, all the situation can be handled. And it's like, if it's total 5 instructions, I say there's 20 fewer instructions if you combine a BPF program using the area 32 mode. And you run it for the ARC64 actually, or x86. Yeah.
Sure.
So there's some benefits.
So it seems to me like the problem is hard enough and difficult enough. So we need to solve it step by step. It seems we're on the same page that jump 32 will be useful for like 32-bit and potentially even for 64-bit architectures. Let's do that because it already will help ARM32 and NFP, my understanding, just extending the ASA. And we'll see how much it helps. And there's a next step. We will do this, some of this.
Yeah. Okay.
Does this make sense?
Yeah, I think it makes sense. I think, I need to try to find the good place in the current verifier to do the thing. For example, the jump 32 based approach, then we need to do to generate extra 0 extension, right? For the first approach, this approach, we need to generate extra 0 extension when there is a mode switch, when it's a 32-bit destination used by a 64-bit instruction. So I think the big problem is to handle this, we need to conservatively clear all the information. Then I'm not sure what's the impact. So maybe need some benchmark to say how many situations fall into this one that need to clear all the marks, regenerate extra information.
Sure, but I'm saying like do that as a second step.
Yep.
Like just introduce gem32,
Is a
and this will be like a natural extension. It's
Yep.
obviously more work for interpreter for all the JITs and for verifier, but it's just like fits naturally what we already have, right? The verifier will check it normally, not much extra logic like anywhere. It's more mechanical addition to the ISA, and see how much it helps to reduce the size of the program just having this instruction. Well, LLVM chain would need to change as well, of course. So it's several pieces together, but I think it should already help, right?
Yep. Yes. Okay. Yeah, I got LLVM change ready, I think, on my local machine. Yeah, but I need to teach verifier to understand these instructions. Then,
Any comments? Time.
Okay. Thank you.
Thank you.